What is IoT? The Internet of Things. Welcome to the fascinating world of the Internet of Things, or IoT. In today's video, we'll embark on a journey exploring the evolution, applications, and future prospects of this transformative technology. Join us on this journey through the interconnected world of IoT. In the video, we'll dive into the world of the Internet of Things, IoT, and learn about important things like: what is IoT? The development of IoT. The evolution of IoT from the 1970s to today. The rise of IoT technologies that paved the way. Top IoT applications. The pros and cons of IoT. IoT standards. The challenges of IoT. Privacy concerns in IoT. Data storage and analysis. The future of IoT, where to next. And finally, the economic impact of IoT. Before we dive into the fascinating world of the Internet of Things, make sure to subscribe to our YouTube channel, Enlighten JEE, where we explore the exciting world of engineering and technology. Now, let's embark on this journey through the interconnected world of IoT together. What is the IoT? The Internet of Things, IoT, refers to the network of interconnected physical devices, vehicles, appliances, and other objects embedded with sensors, software, and connectivity, allowing them to collect and exchange data. This enables these devices to communicate and interact with each other, providing new possibilities for automation, monitoring, and control in various applications and industries. The development of the IoT. The Internet of Things, IoT, evolved from early concepts in the late 20th century. It gained momentum with advancements in RFID, sensor technology, internet expansion, IPv6, wireless tech, cloud computing, standardization, data analytics, and AI. The integration of these elements led to the widespread connectivity and application of IoT across industries, influencing how we interact with technology. The IoT from the 1970s to today. The concept of the Internet of Things, IoT, has roots in the 1970s, and its development can be summarized in key phases. 1970s to 1990s. Early concepts and RFID. Early discussions and concepts of interconnected devices. RFID technology plays a role in tracking and identifying objects. 2000 to 2010. Emergence and connectivity. Advancements in sensor technology and the increasing use of RFID. The term Internet of Things gains popularity. Widespread Internet adoption and improvements in wireless technologies. 2010 to 2020. Proliferation and integration. Significant growth in the number of connected devices. Standardization efforts for IoT protocols. Cloud computing enables scalable storage and processing of IoT data. Increased focus on security and privacy concerns. Rise of Industry 4, integrating IoT with manufacturing processes. 2020s. Continued expansion and 5G era. Ongoing proliferation of IoT devices across various industries. Integration of 5G technology for faster and more reliable connectivity. Advancements in AI and data analytics enhance IoT capabilities. Further exploration of IoT in smart cities, healthcare, and sustainable technologies. Throughout these decades, the IoT has evolved from conceptual discussions to a ubiquitous and integral part of modern technology, impacting how we live, work, and interact with our surroundings. The rise of the IoT. Technologies that made IoT possible. The rise of IoT was made possible by the convergence of several key technologies. Wireless connectivity. Advancements in wireless technologies, including Wi-Fi and Bluetooth, enabled seamless communication between devices. Sensor technology. Developments in sensor technology allowed devices to collect real-time data, making them capable of sensing and responding to their environments. Internet expansion. The widespread availability and adoption of the Internet provided a global infrastructure for devices to connect and communicate. IPv6 implementation. The adoption of IPv6 expanded the number of unique IP addresses, accommodating the growing number of connected devices. Cloud computing. Cloud platforms provided scalable storage and processing capabilities, allowing for efficient management of the massive data generated by IoT devices. Data analytics and AI. The integration of data analytics and artificial intelligence enabled meaningful insights to be extracted from the vast amounts of data collected, making IoT applications more intelligent and adaptive. Standardization efforts. Various organizations worked on standardizing protocols, enhancing interoperability and security among IoT devices. Miniaturization. Shrinking the size of electronic components and making them more energy efficient facilitated the integration of IoT technology into various devices. Edge computing. Processing data closer to the source, at the edge, rather than relying solely on centralized cloud servers improved real-time decision-making for IoT devices. 5G technology. The advent of 5G networks provided faster and more reliable connectivity, supporting the increasing demands of data-intensive IoT applications. The combination of these technologies has fueled the growth and widespread adoption of IoT, transforming it from a conceptual idea to a pervasive and impactful reality. Top IoT applications. Smart home automation. IoT devices enable control and automation of home systems like lighting, thermostats, security cameras, and appliances. Industrial IoT, IIoT. IoT is widely used in manufacturing and industrial processes for monitoring equipment, optimizing operations, and predictive maintenance. Healthcare IoT. Applications include remote patient monitoring, wearable health devices, and smart medical equipment, enhancing patient care and health management. Smart cities. IoT contributes to urban planning, traffic management, waste management, and public services, making cities more efficient and sustainable. Agriculture IoT, AgTech. Precision farming uses IoT for crop monitoring, soil analysis, and automated machinery, optimizing agricultural practices. Retail IoT. Enhances customer experience with smart shelves, inventory tracking, and personalized marketing through IoT-enabled devices. Connected vehicles. IoT applications in the automotive industry include vehicle tracking, predictive maintenance, and in-car entertainment systems. Energy management. IoT helps optimize energy consumption in buildings, industries, and utilities, promoting energy efficiency and sustainability. Logistics and supply chain. Utilized for real-time tracking, monitoring, and optimization of goods in transit, reducing delays and improving efficiency. Environmental monitoring. IoT sensors are used to monitor air and water quality, weather conditions, and natural habitats for environmental conservation efforts. These applications demonstrate the diverse impact of IoT across various industries, enhancing efficiency, safety, and overall quality of life. The pros and cons of the IoT. Pros of IoT. Efficiency. Optimizes processes and enhances efficiency in various industries. Convenience. Enables remote monitoring and control, adding convenience to daily life. Cost savings. Improves resource utilization and reduces operational costs. Data insights. Generates valuable data for analysis, leading to informed decision-making. Automation. Allows for automation of repetitive tasks, increasing productivity. Enhanced services. Facilitates the development of innovative and personalized services. Improved safety. Enhances safety through monitoring and alert systems. Sustainability. Supports eco-friendly practices through smart resource management. Cons of IoT. Security concerns. Raises issues regarding the security and privacy of sensitive data. Interoperability. Challenges arise with compatibility and standardization among devices. Complexity. Integrating and managing a vast network of devices can be complex. Dependency on connectivity. Relies heavily on stable and widespread connectivity. Data overload. The sheer volume of data generated can overwhelm systems. Initial costs. Implementation costs for IoT infrastructure can be high. Lack of standards. Inconsistent standards may hinder seamless integration. Potential for misuse. Vulnerabilities may be exploited for malicious purposes. Balancing the benefits and challenges is crucial for successful IoT adoption and addressing concerns related to security, privacy, and standardization. IoT standards. Several standards and protocols have been developed to ensure interoperability and security within the Internet of Things (IoT) ecosystem. Some key IoT standards include MQTT or Message Queuing Telemetry Transport, a lightweight and efficient messaging protocol for communication between devices in a publish-subscribe model. COAP or Constrained Application Protocol. Designed for resource-constrained devices, COAP is used for simple and efficient communication in IoT applications. HTTP and HTTPS or Hypertext Transfer Protocol Secure. Widely used for web communication, these protocols are increasingly applied to IoT devices for data transfer. IPv6 or Internet Protocol version 6. With a larger address space, IPv6 supports the vast number of devices in IoT, overcoming limitations of IPv4. Bluetooth Low Energy or BLE. A wireless communication standard suitable for low-power devices, commonly used in IoT applications like wearables. Zigbee. A low-power, short-range wireless communication standard for connecting IoT devices, often used in smart homes and industrial applications. Z-Wave. Similar to Zigbee, Z-Wave is a wireless communication protocol designed for home automation devices. Thread. An IPv6-based, low-power, wireless mesh networking protocol commonly used in smart home devices. LoRaWAN or Long-Range Wide Area Network. A low-power, wide-area networking or LPWAN protocol suitable for long-range communication in IoT applications. 1M2M. A global standard for machine-to-machine or M2M and IoT communications, aiming to provide a common framework for IoT service platforms. These standards help ensure compatibility and seamless communication between various IoT devices and platforms, fostering a more interconnected and interoperable IoT ecosystem. The challenges of IoT. Security concerns. Vulnerabilities in IoT devices can lead to data breaches and privacy issues. Interoperability. Lack of standardized communication protocols hinders seamless integration of diverse devices. Complexity. Managing a vast network of interconnected devices poses challenges in terms of scalability and maintenance. Connectivity issues. Dependence on stable and widespread connectivity can be a limiting factor. Data overload. The sheer volume of data generated by IoT devices can overwhelm networks and systems. Privacy issues. Collection and use of personal data raise concerns about privacy and consent. Standardization. Inconsistent standards across industries and devices hinder widespread adoption. Power consumption. Many IoT devices rely on batteries, posing challenges for energy efficiency and sustainability. Costs. Implementation costs can be high, limiting accessibility for certain applications. Ethical concerns. Issues related to the ethical use of IoT data and potential misuse of technology. Addressing these challenges is crucial for the successful and ethical deployment of IoT technologies across various sectors. Privacy concerns in IoT. Data collection. Extensive data collection by IoT devices raises concerns about the amount and types of personal information being gathered. Data ownership. Ambiguity exists regarding who owns and controls the data generated by IoT devices, leading to potential misuse. Data security. Vulnerabilities in IoT devices may expose sensitive information, risking unauthorized access and data breaches. Surveillance concerns. IoT devices, especially in smart homes and cities, can inadvertently lead to increased surveillance, impacting personal privacy. User consent. Clear and informed consent mechanisms for data collection may be lacking, raising ethical concerns about user awareness and choice. Profiling and targeting. The use of IoT data for profiling and targeted advertising may compromise individual privacy. Third-party access. Sharing data with third-party services and applications can introduce additional privacy risks. Data retention. Prolonged storage of IoT data without proper measures can lead to privacy issues, especially if outdated or irrelevant. Inadequate regulations. The absence of comprehensive and updated privacy regulations for IoT devices can leave users vulnerable. Ethical use. Ensuring ethical and responsible use of IoT data remains a challenge, with potential for unintended consequences. Addressing these privacy concerns is essential for fostering trust and ethical practices in the development and deployment of IoT technologies. Data storage and analysis. Massive data volume. IoT generates vast amounts of data, requiring scalable storage solutions. Real-time processing. Immediate analysis is crucial for applications like predictive maintenance and real-time monitoring. Edge computing. Processing data closer to the source, at the edge, reduces latency and enhances efficiency. Cloud computing. Scalable cloud platforms facilitate storage, processing, and analysis of IoT data. Data security. Protection of IoT data is vital, requiring robust encryption and access control measures. Data quality. Ensuring the accuracy and reliability of IoT data is essential for meaningful analysis. Interoperability. Integration of diverse data formats and sources requires standardized protocols for effective analysis. Costs. Storing and analyzing large volumes of IoT data can incur significant infrastructure costs. Data lifecycle management. Efficient handling of data from collection to disposal is crucial for optimal resource utilization. Privacy considerations. Compliance with privacy regulations is necessary when storing and analyzing personal data from IoT devices. Strategically managing data storage and analysis is pivotal for extracting valuable insights and maximizing the benefits of IoT applications. The future of IoT. Where to next? The future of IoT holds exciting possibilities and trends. 5G integration. Widespread adoption of 5G will enhance connectivity and support the growing number of IoT devices. Edge computing advancements. Increased focus on processing data at the edge for faster response times and reduced latency. AI and machine learning integration. Greater use of AI for more intelligent and automated decision-making based on IoT data. Blockchain for security. Blockchain technology may play a role in enhancing the security and integrity of IoT data. Increased industry collaboration. More collaboration between industries and standardization efforts to improve interoperability. IoT in healthcare. Continued growth with remote patient monitoring, smart medical devices, and healthcare applications. Smart cities evolution. Further development of smart city initiatives for efficient resource management and improved urban living. Sustainability focus. IoT contributing to sustainability efforts through smart resource management and environmental monitoring. IoT in agriculture. Continued advancements in precision farming and agricultural IoT applications. Enhanced user interfaces. Improved user experiences through more intuitive interfaces for interacting with IoT devices. The future of IoT involves a seamless integration of technologies, contributing to more intelligent, efficient, and connected environments across various sectors. IoT's economic impact. McKinsey Global Institute projects a potential annual contribution of $3.9 trillion to $11.1 trillion to the global economy by 2025. These figures highlight the transformative potential of IoT across various sectors, promising substantial economic value and continued expansion in the coming years. So, that's the wrap on our journey through the Internet of Things. IoT. From its inception to present applications and future possibilities. We explored its evolution, key technologies, top applications, pros and cons, standards, challenges, privacy concerns, and economic impact. Subscribe for more insights, like if you enjoyed the journey, and share your thoughts in the comments. Until next time, stay curious and stay connected in the world of IoT.